Welcome, ladies and gentlemen, to this presentation. First, let me introduce myself. My name is Florian Kalkowsky. I'm a member of the working group Mechanical Joining Technology at the Fraunhofer IGP Rostock, Germany. Today, I'm here to talk to you about the extension of the application limits of blind fasteners for joining high-strength steels in metal lightweight constructions. During this presentation, I want to talk about the shown points. First, I want to start with some application examples, go on with the design rules according to the Eurocode 3, followed by latest research results from tests on blind rivet connections with high-strength steel to determine the bearing resistance and the fatigue resistance. And finally, I would like to give a summary and an outlook. Here you can see two application examples of lightweight steel constructions where blind fasteners were used to join components made of high-strength steel. On the left hand, we have such high-rack warehouses with slim profiles. On the right hand, we have a roof cladding of a fermentation plant. And if we now look a little bit more detail inside this construction, we can see because of the used high-strength steel, we can realize small connection sizes, but with that fact, we have a problem with the static strength verification because it's not covered by the standard. Here you can see the design rules according to the Eurocode 3 for the static and the fatigue strength verification of connections with mechanical fasteners. If we look at the static strength verification, we can see that for connection with bolts is a full analytical verification possible. In contrast, for the connection with blind rivets, only the bearing resistance can be calculated. The shear resistance needs to determine by experiment. In addition, the equation to determine the bearing resistance is bonded to additional limitations. For example, the components may only have a maximum tensile strength of 550 Newton per square millimeter. So this means that application with high-strength steel fall outside this range. For the fatigue strength verification, it should be noted that there are no detail categories for blind fasteners and connections, and also the increasing material strength when using high-strength steel isn't considered in this verification. For the determination of the bearing resistance of blind rivet connections, we use the test machine SWIG rule Z400E and the test arrangement according to the ECCS recommendations. Also described in this ECCS recommendations is the test procedure with a specific test speed and also a free measurement length to determine the deformation or the displacement inside the joint during these tests. The tested joints were supported one-sided and double-covered symmetrical joints where we use different steel grades of the sheet materials. The steel grades were S235 up to S700. For joining this sheet material, we use different types of blind fasteners. For the evaluation of the test results, we use the load bearing coefficient, which is the result of the maximum test load, the whole bearing area, and the observed ultimate strength. And if we now compare this value of the load bearing coefficient with the design quantile according to the Eurocode 3 part 1 minus 8, we can see all test results are above this design quantile, so we can sum up that the design rules for both joints or connections according to the Eurocode 3 part 1 minus 8 are also applicable for blind rivet connections. In this case, where we have a bearing failure of the sheet material. Due to the missing detail category for blind rivet joints, we carried out fatigue tests to determine the detail category. As a reference, we used connections with a bolt where we have a detail category according to the Eurocode 3 part 1 minus 9. Furthermore, it was assumed that when we use high-strength steel for the sheet material inside the joints, we have an increasing fatigue resistance, which is currently not taken into account by the Eurocode 3. So this had to be proven by tests. If we now have a closer look at the test results and their S-N curves, we see there's a clearly deviation of the fatigue resistance in our fatigue test, and the resistance value of the detail category was a value of 50, and also the slopes from the statistical evaluation deviate significantly in comparison to the normative slope with m equal to 3. If we now compare the values of the detail categories between series 1 and 2, so the series where we use the bolt and the blind fastener inside the joint, we can see, okay, they have a similar fatigue resistance with a value from 100 to 104. And if we now use a high-strength steel inside the joint with blind fastener, the fatigue resistance increased from 104 to 172. So there is a direct link between the used material strengths and the fatigue resistance of the joint. And also for the configuration with 2 blind fasteners inside the joint, we can see there's an increasing fatigue resistance. As I already mentioned, the slope clearly deviates from the normative slope m equal to 3. So we recommend that for non-welded components, a constant slope of m equal to 5 should be used. For the further evaluation of the results, the approach according to the FKM guideline was used. This FKM guidelines allows to determine the fatigue resistance of a construction or a component with a synthetic Wöhler line approach. And this value from the FKM guideline can be converted into a detail category according to the Eurocode 3 by this shown equation. And for this approach, according to the FKM guideline, some input parameters are required. For example, the SCF, a stress concentration factor, and we used numerical simulation to determine the stress concentration factor. And as you can see in the diagram, there is a linear relationship between the SCF and the geometric parameters of the joint. And with these input parameters, we determine the fatigue resistance according to the FKM approach. And as you can see, the FKM guideline take into account the increasing fatigue resistance when we use material of a higher strength. And if we now directly compare the detail categories from our test with the detail categories determined by the FKM guideline, we can see there is a really good conformity of experiment and the FKM guideline, and there are not really big deviations between the results, and so we think that this approach or this way to determine the fatigue resistance of such joints is a really good thing. Let me summarize again the things that have been shown. It was shown that the design rules for bearing type connection with bolts are also applicable to connections with blind rivets despite the use of high-strength steel. Also, by following the FKM guidelines, the fatigue strengths of the bearing type connections could be described very well, but transfer to steel construction is not possible without further ado. There are influences in the manufacturing process which are unknown. For example, we have such marks on the components which directly influence the fatigue resistance, and also, or furthermore, the delta sigma concept should be retained. And below you can see two standards with already have the delta sigma concept in their approach. The first standard defines the fatigue resistance of non-welded components as a function of the yield strength of the used material. And the second one take into account several influencing variables in the verification of the fatigue strength, as you can see here in this equation. We would like to thank the European Research Association for Sheet Metal Working and the AIF, which funded this project. And also, we would like to thank our project partners for their support during the project period. Thank you for your attention, and don't hesitate to ask us your questions. You can also send us an email afterwards. Thank you.